All right, so this is Module 4, and if we remember back to the last module, we were looking at the syntax, the expressions, and notably how to write literal values of different types of data within a C++ program. So we saw the literal representation of an integer, of a double with just a decimal place. Importantly, we saw the literal representation of strings, which had a double quote around a bunch of characters. A single quote can surround a single character, and that would be a character data type. And we also saw literals for Booleans. Today we're really looking at data types in more detail. What are the different data types available in C++? What are they called? We're going to see a whole bunch of different keywords that are reserved for those data types. And we're also going to look at how do we use memory. Right? So up until now, the programs that we've really seen have simply printed out any data that we computed with an operator, with a plus sign or a division sign. Now we're going to try to use memory to store and remember values, and that's very intertwined with the concept of data types. All right, so I will remind you about what a computer does. And one of the first things that we covered in this course was that computers really don't do much. They do arithmetic, and they remember numbers. And how they remember numbers was using devices similar to the flip-flop, a simple circuit that can hold a charge. It can hold a charge of 1 or 0. And we explained that for any piece of data, really it's just a series of 1s and 0s with each bit, each 1 or 0 digit, representing some sort of a physical electrical device that can hold that state. So main memory, or RAM, consists of a huge array of bits that can be changed to 1 or 0. And it's how those bits are arranged and how those bits are grouped that allows us to store different types of data and to actually interpret those 1s and 0s. So one of the fundamental units of memory, we don't typically think of memory in terms of individual bits. We normally think of it as a series of bytes. A byte is just a group of 8 bits. So there's nothing specific, there's nothing different about a byte. A byte is just a logical grouping of 8 consecutive bits in memory. Now each byte is readable and writable. So the hardware itself inside a computer allows you to, if given an address of a particular byte, so say byte number 4000 or 42,391, you can read the value from that and you can bring that into a register. And we talked about how registers are where we hold data temporarily so the CPU can actually perform computations on it. So we might have an instruction that says, well, go read the binary byte, the series of 8 bits, out of address 42,391 and store it in register 2. And then we might do a computation and get an answer, and we might want to write that answer back to byte number 42,391. So each individual byte within main memory is addressable, and we've got billions of bytes. A typical machine that you can buy today for a reasonable price might contain 4 to 8 billion different bytes of memory. Each individual byte of memory has a specific address, a numeric address. So there's quite a bit of them. Now, bytes with 8 bits are somewhat limited. They're just a sequence of 8 binary digits. But somehow or another, and we've talked about this early on in the first module, the first 2 modules, a byte can somehow store integers, but it can also store booleans and characters and actually even color values and strings and all sorts of different data. And the question is, well, how? There are no bytes in main memory that are dedicated to holding integers. There's no bytes in main memory that are specifically designed to hold colors. They all just hold binary 1s and 0s, 8 binary 1s and 0s. The reason we can give the illusion that the computer can store all this different type of data is that we tell the computer how to interpret the bytes, how to interpret the binary numbers that we store. So a particular number might correspond to a color if we know that that particular byte should be interpreted as colors. In addition, we're often going to have to group consecutive bytes together to hold larger pieces of data. So I think that we talked a little bit about binary numbers and how the size of a number that you can hold in binary is based on how many digits you have available to you. So if you have 3 digits, you've got 0, 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. It's only 8 different options. On 8 binary digits in a byte, you can hold 2 to the 8th. So the highest actual number, if you go to 2 to the 8th in a calculator, the highest actual number you can hold within a byte is 255. That's certainly not going to be usable for our system. We're going to have to pool our bytes together. So maybe we can put 4 bytes together and have 32 bits to hold larger numbers, 64 bits to hold even larger numbers. So it's the grouping and it's the interpretation of the bytes that forms the concept of a data type. When we declare data, or we reserve space in memory to store pieces of information, we hold the data type, or we actually explain the data type to the computer. And then later on in our program, when we access it, we are actually accessing groups of bytes and the interpretation or the format of those bytes. So possibly the simplest type of data that we can have is a straight character. And the table that I just popped in here on this slide represents the ASCII character set that we discussed a few modules back. So it turns out that the ASCII character codes, there's only 128 different unique characters. So actually 2 to the 8th is 256. So let me actually change that and just say that 2 to the 8th is greater than 128, meaning that we can actually store all the numbers between 0 and 128 within a single byte, within 8 bits. We actually only need really 7 bits, but that's okay. So we won't actually address memory in any smaller units than one physical byte with 8 bits. So a character, a char, just char, however you're going to pronounce it, that particular data type, and that's a keyword in C++, that data type refers to a specific byte that from now on, once you start using that byte, will be interpreted as an ASCII character code. And so if you try to print it out, if it's got the number 66 in it, it's going to print out the letter B. If it's got the number 98 in it, it's going to print out the lowercase b. Remember I talked about how C++ is case sensitive. Well, all characters are ultimately held as numbers. In memory, in your program, all they are is just numbers. And looking at this ASCII character set, you can really understand why things are case sensitive. The lowercase letter b and the uppercase letter b, to us, sort of mean the same thing. We know that they're sort of the same letter, just possibly being used in a different context. But from the computer's point of view, it's 66 and 98. There's no concept of those being related at all to each other. So in main memory, we would hold characters, data types, as integers in binary, but we would display them and we would interpret them as characters. Character data types are used frequently, but we probably won't use them for a little while. One of the most common types of data that we will use, we've already used, is integers. So from regular mathematics, we know integers are whole numbers with no fractions. For a computer, there's actually several different types of integers. The first type, and the simplest one, the smallest one, is called a short. So in a short, we actually can hold integer values up to, or in terms of magnitude, 2 to the 15th. So that ends up being 32,768. Now where do we get that number from? Well, it turns out that a short holds 2 bytes, or it groups 2 bytes together, 2 consecutive bytes within main memory. So it has 16 bits available to it. And it just holds a regular binary number. The reason we have the 15th instead of 2 to the 16th in a short is that there's a sign. We can hold negative 2 to the 15th all the way up to positive 2 to the 15th. The leftmost bit of that 16 consecutive bits, or those 2 bytes, can be a 0 or 1, just like any other bit. but the leftmost bit is reserved for representing a plus or a minus. A 0 in the leftmost bit of a short represents a positive number. The 15 bits to the right represent a positive number. If there's a 1 in the leftmost bit of a short, then the 15 bits to the right represents a negative number. All right, so that gives us a numeric range of plus or minus 32,000, roughly 33,000. We can also have an unsigned short. So we've got keywords called short. We've got keywords unsigned space short that holds values from 0 to 65,000. All this does is say that this particular short, this type of value, can only be positive. And that one bit that we reserved formally for a plus or a minus, or 0 or 1 to represent our plus or a minus, is now actually used for data. So now we've got basically just 32,768 times 2. Right? And that's the largest number that we can hold. So let's think about a little bit about how the computer would differentiate between character types and shorts. So I'm going to go over and draw a really crude diagram of main memory. So we've got our main memory system here. We'll call it RAM. And let's divide main memory into a series of bytes. And of course, we're not going to draw all of them here, but we would typically have billions of these bytes. But we'll think of main memory as a grid. And each one of our bytes are numbered, right? So 1, 0, 1, 2, 3, 4, 5, 6, 7, and you can kind of get the picture. We're going to number each one of our bytes. So we'll get a little ahead of ourselves in terms of syntax, but when we declare a variable of type character, right, what we're going to do is we're going to reserve one particular byte, because a character occupies one byte. Right? And we can use that variable, and again, we'll come back to this diagram in terms of the syntax of assigning this variable later on. If I switch to another color here, if we declare an int, or a short, sorry, the computer is going to go find 2 consecutive bytes, any 2 bytes, right? And that's important to remember, any 2 bytes. 2 consecutive bytes that it can use for that particular short variable. Right? And again, we'll go back to how do we assign that variable shortly. But essentially, we're grouping these data types together, and then this value could be 0, 1, 1, 1, 0, all the way out to 16 bits, right, to represent that short. Now, a short, or an unsigned short, is fairly limited in terms of 32,000 and 65,000. Those are fairly big numbers, but certainly we would want to write programs that could calculate values higher than that. So the next type of data that we have, and probably the most commonly used type of data within this course, is an int, an integer. So whenever you see that keyword int, that really just means we're talking about integers. And we've seen that actually in a little bit of a strange context in front of the main function, and we'll talk about that later in the semester. Now, an int is the consolidation or the combination of 4 bytes, 4 consecutive bytes in memory, giving us 32 bits. It works the same way as a float, as a short, sorry. Where the last bit, or the leftmost bit, is reserved for 0, 1, indicating a positive or a negative. So we actually have minus 2 to the 31st power all the way up to plus 2 to the 31st power. The numeric range for an int, based on that 32 bits, is well over 2 billion, or over 2 billion, plus or minus over 2 billion. If we do an unsigned int, that just means that that last leftmost bit is not reserved for signs, and that the unsigned int can only hold positive numbers. And again, if you know for sure that you are only going to be using positive numbers, this data type makes sense. Now we've got double the size of a value, so we can hold values from 0 to around 4 billion. Again, the reason we've got these caps, the reasons we have these limits, is that when we reserve just 4 bytes, that means we've got 32 bits, we've got 32 digits in binary. If we're thinking in a 10-base system, if I told you that we had only 4 digits to work with, if you were going to write a number on a sign that only had a certain amount of space on it or something like that, if I said you had 4 digits, you'd know that the highest number that you could show was 9,999. The reason these numbers look so bizarre is because the limits are actually calculated from binary. Right? So 2 to the 31st power is not necessarily a nice round base number, or 10-base number. Now, we also have longs. I haven't really talked about this explicitly, but long data types and unsigned long work similarly as ints. Nowadays, on most systems, they tend to be the same size as ints. On smaller systems, longs would be 32 bits, and ints would be 16 bits, and shorts would be 8 bits. C++ doesn't really actually promise that integers are going to be 4 bytes. Or that shorts are going to be 2 bytes. Really, C++ only promises that an int will definitely be as large or larger than a short, and that long will be as large or larger than int. And so if you were really worried about how big of a number that you could store inside of an integer, you can use a built-in operator, a built-in function in C++ called sizeof. So sizeof will always return back. It'll evaluate to the number of bytes reserved for a particular type of data. So you'll notice the syntax here, we've done a cout statement, but instead of a normal expression where we printed out a string, I'm calling a function called sizeof. And the parameters to this function is the data type. Now the idea of a function, the idea of parameters is something that we're going to cover later on in the semester. For now, you can just think that it gives you an answer. All right? It evaluates, just like 3 plus 4 somehow evaluates to 7 through the CPU. The sizeof operator is going to evaluate to 2 for short, for 2 bytes. And we can run this on this computer. We can run that program. It's not necessarily the same on every machine. We switch over here. I'll run it. And we can see on this machine, I've got 2 bytes reserved for a short, 4 for an int, and 4 also for a long. And again, on your machines, that might vary. That tends to be the most common case. Integers aren't the only types of numeric data that we can store. We can store decimal numbers. So we talked a lot about integer division in the last module. And we know that there's definitely different hardware that's responsible for floating point numeric operations as opposed to integer operations. And one of the reasons this is that for floating point operations, the regular binary format of numbers that we've seen already, and I've gone through with you before, doesn't really fly for decimal values. So there's actually a fairly complex standard. It's the IEEE 754 format, or for scientific notation in a binary numbering system. It's fairly complex, and it's totally different than the normal binary. It's still, of course, just ones and zeros, but those ones and zeros are interpreted quite differently. Because the format of those binary numbers is different, we require different hardware, and of course we have to interpret them differently. So a float is the smallest type of decimal number that you can store. It occupies 4 bytes, just like an integer, so it's still 32 bits. However, it stores the values in a different method, in a different way. And a float value can be plus or minus 1.79 times 10 to the plus or minus 308th power. Very, very large numbers with a lot of precision left over for it. Now, if you need more than that, which is not too terribly uncommon, a double will give you 8 total consecutive bytes, giving you much more room for your numbers. Right? So that'll give you 64 bits in the IEEE standard, and that's going to be 1.18 times 10 to the plus or minus 4,932nd power. astronomically big numbers. It's very unlikely that you'll need numbers larger than can be held inside of a double. And again, this is just recommendations, this is just examples. It's not necessarily going to be 4 bytes on my machine and 8 bytes on my machine, but we know that double is always going to be guaranteed to be at least as big as float. And we can switch over here and add these statements. Give that a run. And we do see that it comes out to be 4 bytes and 8 bytes on my machine. And again, on a different system, that might be very different. Of course, there are other data types. Booleans are perhaps the easiest data type to store in a binary numbering system. Booleans only have 2 possible values, true or false. Theoretically, we only need 1 bit to store a Boolean value, a 1 and a 0. However, because we always address memory in terms of bytes, we actually do have 8 bits. So you can see the true being 7 zeros and then a 1, and the false being all 8 zeros. Strings, which is a very common data type in most of our programs, we're gonna deal with this a little bit later, but actually there is no native type for strings. Strings are just a lot of characters. And we saw how each individual character can occupy a single byte. A string will be a sequence of bytes interpreted all as characters. So now that we've seen different types of data, we think about this diagram that I started to draw. I mentioned that we were going to come back to, how do we declare and how do we store variables in memory? We kind of get a picture of how it would be organized. Now let's actually talk about, well, how do we remember data? How do we store data? What's the whole purpose of knowing what types of data we can use? So to be able to store data, we have to reserve bytes in memory for storing our information. And again, we've got billions, potentially billions of bytes in our system, and we certainly don't want to get into the business of hand-picking particular byte numbers and how many bytes do we need for a double versus an int. That's something that is deeply ingrained into computer system. The operating system is going to determine a lot of that. The processor architecture is going to determine how many bytes are reserved for each one of these data types. It's a complicated process, and frankly, as a software developer, I don't really care where my variables and where my data is really stored. I'd like to be able to assign names that make sense to me, that I can store my information in. And so that gives rise to the idea of a variable, which is very similar to any kind of other, anywhere else that you've talked about variables in algebra or anything. So the way we declare a variable, and the declaration of a variable is very important. We have to declare, we have to tell the computer ahead of time that I would like to reserve a piece of memory. Right? And if I want to reserve a piece of memory that stores an integer, I declare it by saying int, the keyword int, space, and then some name of my variable. And my variable name can be anything that I want. There are a few rules. They cannot have spaces in variable names. That's very important. And we've talked on several occasions on how we try to avoid spaces whenever we can. When we're programming in any context, it tends not to work very well. This is a prime example where it's a compiler error, and it's actually kind of nonsense excuse me, to have a variable which has spaces in it. So variable names cannot have spaces. They can be words. If the words are, if there are multiple words within your variable name, the common way of doing that is to separate them with an underscore, an underline, or by capitalizing the first letter in each word. Your variable names cannot start with any special symbols other than an underscore or a number. It cannot start with a number. After the first letter, you're allowed to use any different character, alphanumeric character, but no special characters like commas and semicolons and periods and hashtags and that kind of stuff. So just alphabetical or numeric values. So if I want to declare a variable of type int, I can do that, and I'm naming it x. If I want to declare a variable of type double, I can declare that ahead of time as double y, character C. Same deal. This variable declaration, notice, has got a semicolon at the end. It's a statement. It's actually causing the computer to go through memory and find a byte that's not being used for character C. It's finding a byte or 2 bytes in memory that can be used for now short y. Now once we declare these variables, I can start assigning data to them. All right, so in this slide, I've got an integer x being declared, and I'll just point out that there's some syntax variations, and if you look in the textbook, they'll go over quite a bit of different rules on how to declare variables. We may declare variables all on one single line. We may declare multiple variables of the same type just by separating them with a comma. There's no rule that we have to do that. We could have also done it here. Technically, this is a syntax error. I can either define it here or I can define it separately, but I cannot redeclare 2 variables of the same type. And so I'll remove that. I've declared C, and once these variables have been declared, if I want to put data into the variables, I use an equal sign. Now the equal sign in algebra is sort of a little bit easier to work with. And let's switch over here and have a blank slate. In algebra, we might very well say x equals 5. Let me switch over to a better color here. Or we might say 5 equals x. And in algebra, these are equivalent. There's really no difference between the two. So I'll say algebra. In C++, 5 equals x is a big no-no. We're not going to be able to do that. In C++, this equal sign is an assignment operator. It's not an equal sign per se. It's not an equivalency. What it's really doing is it's causing the computer to do something. Remember, these are statements, and in C++ we're going to have a semicolon at the end of this. What it's doing is it's causing an action to occur. It's causing, if we draw main memory here, we'll call it RAM again, we've already declared a variable called x, and I'll just draw it as a separate little box. I don't know which number it might be referring to. It could be address 126. All right, that's not really that concerning to us. But we've declared x. We know that it has a set of 4 reserved bytes in it. What this statement does is it causes the number 5 to be copied in binary to that location. It's an actual movement of data from the right to the left. So the assignment operator can be used with any of our variables. We can reassign variables, so I can assign W into C. I can assign the character 6. Right? And remember, the ASCII character code system works with numerics as well. Any key on the keyboard has an ASCII character symbol that represents it. So the symbol 6 can be stored over into C. And again, if I go back here, if I later on said, okay, well, now I want x to equal 2 plus 2, I could do that. Right? This would be evaluated and set to 4, and then the value in x would be changed to 4. So we can reassign variables without any problem. Z can be assigned to different variables, right? So y is 7.8. The right-hand side of the assignment operator is always fully evaluated, so it can be a mathematical expression, 2 plus 2. It could be a variable, and that variable is automatically read. So if I say z equals y, what I'm really saying is copy whatever data is in y, which is 7.8 right now, and take that 7.8 and put it into z. Over here, I'm saying z is now equal to y plus 1.7. So I'm taking the value in y, the 7.8, and I'm adding 1.7 to it and storing the sum into z. So for our first real big programming example, I want to use these variables, and I want to use the mathematical expressions that we've already worked with, principally integer division and modulus, to build a program that prints out the total amount of time since January 1st, 1970. And what I'd like to do is use the modulus and division operator to, instead of saying how many milliseconds have passed, or how many seconds have passed, to actually tell us how many hours, minutes, and seconds have passed since this time. And it seems like sort of an arbitrary time, January 1st, 1970. Computer systems, the Unix operating system, it's been around for many decades. The Unix operating system defines the start of time, sort of euphemistically, as January 1st, 1970. That's a date previous to the first version where this library for time was written. And it's not really saying that time began in 1970. What it's really just establishing is a reference point. So we can ask the computer what time it is, and it doesn't really answer us in terms of time zones and minutes and hours and all that stuff. It simply will tell us how many seconds have passed since this particular date. And every computer system across the world will always know what time it is based on that one reference point. It's a standard, that's all it is. It doesn't really change the way we work with time. And the way we find this value, the way we find the number of seconds since 1970, is by saying time. All right, calling a function called time and passing 0 into it, and that's a little bit beyond the scope why it's 0. We'll eventually talk more about parameters later on. So we've seen actually two sort of functions, size of, and now we're seeing time. To be able to use time, we need to include the ctime library. The reason these libraries are prefixed with C is that they're actually written in the language C, not C++. So that kind of predates C++ a bit. So let's take this code, and I'm going to start with that. So I just copied this into Visual Studio, and we'll start just by displaying the number of seconds. So let me build this, and we'll go and run it on the command prompt. And we see that the number of seconds since 1970 came out to be a very, very large number. So it looks like over a billion seconds here. So it's quite large. So now my question is, I want to print out how many hours and minutes have been, and then of course eventually the total number of seconds, or the remaining number of seconds. So let's break this problem down a little bit. It becomes more of just a problem solving. We have a total number of seconds, and I want to find out how many hours are in that second. So if I said, actually let's back it up to minutes. How many minutes are in this total number of seconds? So let's go back to let's draw a little bit, diagram out this problem. So let's say, I'm not going to take that huge number. It's kind of awkward to deal with. But let's say I've got 71 seconds. And let's think about, all right, well, how do I figure out how many minutes are within that number of seconds? Certainly we would do, we think about dividing 71 by 60. And that would give, 1 point something back. But remember that because these are integers, 71 divided by 60 is actually going to give us just the 1. All right, it's going to give us exactly 1. So 71 divided by 60, if I was to suppose I started with 71 seconds, if I did 71 divided by 60, I would get 1 full minute. If I started with, let's say, 130 seconds, I'd do 130 divided by 60, and that would give me 2 minutes. So in my program, I can divide by, I can take that total number of seconds since 1970, and I can divide it by 60 to get the number of minutes. The question, though, is then how do I get the number of remaining seconds? Right? So I would have 11 seconds here, and I'd have 10 seconds remaining here. And how do we do that? Well, we know that 71 divided by 60 is 1 with a remainder of 11. We know that 60 are divided into 30. If we remember our long division, this is just 2 with a remainder of 10. All right, well, how do we get the remainder option? Do we have an operator that can do the remainder of an integer division? Certainly we do. 130 modulus 60 will give us back 10. It'll give us back the integer remainder. So sort of thinking about this, we can take the total number of seconds, we can divide 60 into it to find the total number of minutes, and we can do a modulus operation of the same numbers to find the number of seconds remaining. So let's go and change our code to actually include that. So we're just starting with minutes right now. And I want to actually store these values in variables. So I'm going to say int minutes and seconds. And again, I've declared minutes and seconds this way. I could have also declared them on a separate line. That's fine too. Minutes is going to be defined as total divided by 60, and seconds is going to be defined as total mod 60. I want to point out the order here. We must declare variables before we use them, before they're actually used down here. The compiler works from the top down, and it'll see that we've declared variables, and then when we use them later on, it will know how to interpret them. If we remove this, Visual Studio tells us there's a problem. We'll certainly have compiler errors as well. And we can see undefined identifier, minutes, seconds. So we need to declare them first. Declaring them, by the way, down here won't help. That won't help the problem because the compiler works from the top down. So they have to be declared ahead of time. We don't need to declare them separately from when we are assigning them. We could also say minutes equals total divided by 60, and seconds equals total mod 60, and that works perfectly fine as well. That's similar to up here. So let's print this out, and I want to, again, as you start to begin programming, some of the common mistakes that I'll see people make is we compute results. We store a result in a variable, and then we run the program, and we wonder why we don't see the results. Remember that C++ only prints out what you tell it to print out. So if I declare a variable, if I declare a variable and I assign a specific piece of data or specific value to that variable, that does not tell C++ to print it out. If I want to print out the number of minutes, and by the way, always get into the habit of labeling your output. If I do cout seconds instead of a label, let's see what that's going to show up as. Always think in terms of the user. When I run this program, minutes comes out to a fairly large number, and certainly there's been a lot of minutes since 1970. Printing out seconds without a label, just 26, is really inappropriate, right? Because we don't know what that's a number without a context. So get used to it right away. Always label your output. Make it clear to the user what you're printing out. Do not assume that the user is me. grading your work. Do not assume that the user is you who knows what the second thing that you printed out is. Assume the user is someone who has no idea what this program is supposed to do. That's critical to keep your mind in that point of view. So if I run this now, I can see that it comes back as, again, a fairly large number. 1 more minute, by the way, has passed since I was talking, but we have a different number of seconds. And if I run it again, we're down to 10 additional seconds. 5 seconds have passed. And if we wait a bit longer, we can see that number changing. All right, so now let's change this to also include the number of hours. So kind of back to the drawing board here. Let's clean this up. And we had, we came back with, let's say we had the 130 divided by 60 gave us 2 minutes. Well, we know that that was seconds. That was the second since 1970. Now, if we look at our command prompt, we have a real big number for the number of minutes. Well, we could do the same thing, and if we had, whoops, sorry about that. If we had, let's say, 82 minutes left over, how would we find the number of hours? Well, it's the same process. We would do 82 divided by 60. Now, the 60 doesn't represent the seconds in a minute. It represents the minutes in an hour, but it's still going to give us the same answer. The 82 mod 60 is still going to give us the 12, but this is the remaining minutes, and this was the hour. And so we can use the same setup as before. And I tend to do my computation all in the same spot. Hours will be minutes divided by 60, not total, because total was the number of seconds. And in fact, I might want to rename that to be seconds since January 1st or something like that. But I'm taking the current number of minutes that I have and figuring out how many hours are in there. And I actually want to reassign minutes to really be minutes mod 60. I'm going to line my output up so the equal signs all line up vertically, just by injecting some spaces. So notice what I've done. I've calculated the number of minutes, but then I've changed that. That was a real big number, and now I've modded out the hours as well. So notice minutes should definitely be restricted between 0 and 59, and seconds should also be. So now when we run the program, I see that I've got a lot of hours since 1970, certainly less, right? 389,000 hours, 30 minutes and 31 seconds. And actually, if I look at the clock on the bottom of my screen, it is 30 minutes past the hour. And I can actually continue through with this and try to start changing hours as well. So we know that we've got 24 hours in a day. So we can compute that. Days equals hours divided by 24. The number of hours we have, lots of hours, divided by 24. That'll give us the number of days. And then hours really becomes hours mod 24. So instead of a whole lot of hours, I'm going to do a modulus of 24, so it's just the remainder. And again, I'll print it out. Right, so we're seeing that we've got 14 hours since the beginning of the day. And again, now you can kind of get an idea of what time it is. Now this is in Greenwich Mean Time, so it depends on your time zone, of course, as well. And again, we can continue through this and we can come out with 365 days per year, which is not exactly true. We'd have to deal with leap years, so we'll stop there. We'll just say that there's been 16,000 days since January 1st, 1970. Now, looking back at the code, you might be looking at this and thinking, well, is this kind of a strange way of doing it? I'm calculating the number of minutes, then I'm changing the minutes. If I was to write this program again tomorrow, I would probably come up with a slightly different ordering to it. If I knew ahead of time that I was also going to compute the days, I might have done the days first. I might have calculated how many seconds are in a day and then just simply divided it out that way. I could have calculated how many seconds are in an hour, 60 times 60, and done it that way. There's a lot of different ways to program this code. And if you look in the textbook, this is actually an example in the textbook. If you look in the textbook, it's done it a little bit differently. One of the valuable things for you to do as you're learning to program, I've said several times earlier in the modules, you learn to program by programming. You don't necessarily learn to program by watching somebody program. You don't know exactly what's going on in their heads. One of the ways that you can kind of learn a lot from looking at code, though, is looking at multiple solutions. So if you compare the solution that I have here with the solution in the textbook and realize that they're essentially doing the same exact thing and understanding why the code is doing the same thing, why is it equivalent, it can actually be very beneficial for you. All right, so let's go back to the slides. And I want to point out something that's very important and is one of the most common problems that I see among students that are just learning C++ and just learning how to program. And it's confusion about the equal sign. So going back to to draw, we are used in an algebra type setting to writing down an equation sort of like a rule. So you might say y equals 2 times x, right? And so when you write something like that down in algebra, and then you go and solve something, you might figure out that, well, x is actually equal to 5, which tells you that y is equal to 10. And if you change x or later on solve x to be 7, because of this formula, because of this rule that you've written down, you would infer that yes, y is equal to 14. The idea in algebra is that you write down equations and that they are rules. They are permanent. There's a constraint such that when x changes, y also changes. That's something that you want to get away from thinking about in terms of programming. So if you fall into that trap, you can get kind of confused with the way programming works. The assignment operator is not a rule. It does not set up a constraint or a relationship between variables. It's a literal action. It takes a value, whatever the value is on the right-hand side of that assignment operator, and it stores it into a variable. If there's a variable on the right-hand side, int y equals x plus 5, y will be assigned the value that x plus 5 is at that particular moment in time. If I was to go and set x to equal 10 later on, and notice that I'm using words like later on, there is a timing aspect of all of this. In a program, one line executes at a time, and then we go to the next line. It's a very, very small amount of time, so it seems instantaneous, but it's not. It's a one-by-one step through this code. So when I say x is equal to 5, y will be 5 plus 5. Y will be 10. The next thing that I do is I reassign x to be 10. That does not mean that y will now be 15. 10 plus 15. Y is 10, and y will be 10 until I change the value of y. And so that's critical that you understand that. When I print this out, x will print out, of course, at 10. If I print out y, y will print out at 10 as well. Variables can be assigned with the assignment operator. We can also use them in equations. We can assign the variables as a result of an equation, so 5 plus 9. We can assign the variable as a result of a function call. We can print out the variable name. Ideally, we should be able to assign a variable's value based on what the user types in as well. And that's the topic that we'll cover next.